This is the review for exam. The first problem in the review is looking at just finding derivatives, and so we'll start by calling this x squared plus 9 over x plus 3 to the 1/2 power. Now that we have that, we can take the derivative of this by saying y prime is equal to, and we bring the power down. You have x squared plus 9 over x plus 3 to the negative 1/2 power, and this whole thing is multiplied by the derivative of the quotient, and we will need the quotient rule for that. So the quotient rule is the low times the derivative of the high term minus the high term times the derivative of the low term all over x plus 3 squared. So this would be your answer, and when they say don't simplify, it would be nice not to simplify. There is, however, another way to approach this problem, and another way to approach this problem is before taking the derivative right away, it might be beneficial to take the ln of both sides. This is the logarithmic differentiation way of doing things. And so you would have the ln of y is equal to the ln of x squared plus 9 divided by x plus 3 all raised to the 1/2 power. So what's the advantage of this? The advantage is that we can take the 1/2 out, and so we would eliminate using the power rule and a chain rule. And there's more. We can actually split up this quotient into a difference, which makes our deriving, taking the derivative, a little bit easier. So if we want to go from here, then remember that this isn't y yet, or it isn't y prime, this is just y. So if we ddx this, we would get 1 over y times y prime is equal to, and now let's just focus on this part right here, and there's a 1/2, big parentheses, and the derivative of each of these terms. So derivative of ln of x squared plus 9 is 1 over x squared plus 9 times the derivative of x squared plus 9. And then the derivative of the ln of x plus 3 is 1 over x plus 3 times the derivative of x plus 3, which is just 1. And lastly, this is not quite over yet, we want to solve for y prime, and that's equal to just multiply everything by y, which is the square root of x squared plus 9 over x plus 3 times this big thing that we got, which isn't so big, and that's 1/2 times 2x over x squared plus 9 minus 1 over x plus 3. So this is your answer for this problem. You also could have had this as an answer. Either of those would work. So when would you want to use logarithms? This is probably in the cusp of whether we should use logarithms or not, because this is not too bad using the chain rule. But it could be quite possible if you have more products in the numerator or the denominator, and you have different powers, for example, you may be interested in using this ln trick just to make things a little bit easier. Let's go to the next problem. The derivative of 2 to anything. So this one we don't need to simplify or anything like that. We can just go straight to our y prime. It turns out that the derivative of 2 to the anything is 2 to the whatever thing that you have. times ln 2 times the derivative of this power. So the derivative of this power is the derivative of 2 sine x is just 2 cosine x plus the derivative of e to the x is just e to the x. So that's a derivative of that power, and there's no more more complicated functions inside any of those, so we don't need any more chain rule. This is it. The next problem is a good problem in trying to distinguish between multiplication and composition. So the first term in this looks like it's a product, so that would be good to note. This is not a product. This is composition, which will invoke the chain rule. So now that we have those two things separated and figured out, let's take the derivative. The derivative of the first term is going to be a product rule. So we look at the first factor. Derivative of cosine is negative sine. So derivative of the first times the second plus the first times the derivative of the second. So that's the first term right there. Plus, now remember that this is a composition. This is a function within a function. So the outer function is a sine function. The derivative of sine is cosine, and then we keep that same function inside times the derivative of the inside, and the derivative of tangent is secant squared of x. So this would be your final answer. And just one more note, just to be absolutely clear, that here we use a product rule, and here we used the chain rule. Product, chain rule. So I hope that was clear, and let's go do some more derivatives. Here are a couple more derivatives. This first one looks like there's a set of terms here. There's 4 different terms that we're going to have to do. And keep in mind that pi is really nothing but a number. So let's see. We have a number raised to some function. So this is similar to the 2 to the x thing that we did earlier. This is a function raised to a constant. So this is this power rule that we're going to do. Here is a function raised to a function. So this is something that we have to take into consideration and probably do off to the side separately. And then finally we have a constant raised to a constant. Well, a constant raised to a constant is just another constant, and the derivative of a constant is 0. Alright, so we're kind of jumping ahead. Let's do this piece by piece. So the derivative of a constant raised to a function power is the exact same thing. Let's call this y prime. So this is pi raised to the sine x power times the ln of pi. Just pretend that pi is equal to 2 and you'll see that this is really what's happening. And then times the derivative of the inside, or the power, the inside function. The derivative of sine is cosine of x. So that's the first part. The second part as noted here, it's like just a power rule. So pi is a number, pi, and then we have sine of x raised to the, subtract 1 from pi. Well, pi is like 3.14. It's an irrational number. So the best way to denote that is just pi minus 1. We're not quite done yet, because after we do the power rule, we have to do the chain rule, which is the derivative of the sine function. And again, that's cosine. Now the third term here is the one that's going to require a little bit of work outside. And why don't we just quickly identify that this is a constant, so the derivative of a constant eventually here will be 0. Okay, but let's go back to this derivative right here that we're going to have to take. So let's call this another function, y, z or something, is equal to sine x raised to the sine x. Now we can't use the power rule because our power is not constant like the previous term. We can't use the exponential rule because our base is not constant like the first term. And so this is where we're kind of forced to take the ln of both sides. So if we take the ln of both sides, then we can take this power down in front, and this will become a product instead of a power within a power. So now what we're going to do is we're going to take the derivative. Let's do the ddx step. And we will get z prime over z, or 1 over z times z prime, is equal to, now this is a product, so derivative of the first, cosine x times the second, ln sine x, plus the first sine x times the derivative of the second. So 1 over sine x times the derivative of the inside, which is cosine x. So it looks like we might have some canceling going on here. And then let's not forget to get z by itself. So we need to multiply by z on both sides. This is sine x raised to the sine x power times cosine x ln sine x plus cosine x. So that's what's going to go in here. If we write small enough, it can fit. Sine x raised to the sine x power times exactly what I just said earlier, and that would be cosine of ln of sine x. Okay, we're out of room. We actually don't need this because we can just say it's equal to 0 up here. Alright, so cosine of ln x, or I'm sorry, cosine of ln of sine x plus cosine of x. Whew, that's it. And that would be your answer for this particular problem. So remember that this is exponential. This is the power rule. And this uses logs. And then that last one over here is a constant, so that just becomes 0. Okay, on to our last one. For this problem, it could take, this is 1, 2, 3, 4, 5, 6, 7, about 7 layers of the chain rule, which can be done, but there is some value in simplifying this expression before we actually take the derivative. And so what I mean by that is that, you know how we, in the previous problem, we rewrote our y to be something to the 1/2 instead of with a square root, for example. And so if there's any way we can simplify this, maybe we should try to take advantage of that. First, we can take a look at this portion of the problem where we see the cosine of the arc cosine of something. Well, it turns out that that little bit will undo each other. So without taking the derivative yet, we actually have y is equal to the tangent of the ln of the cosine and the arc cosine undo each other, and all we have here is the ln of e raised to the arc tan of square root of x. Okay, well, wait, it looks like the ln of e to the something, this is going to undo each other as well. So this is still y equals to the tangent of, now the ln of e would undo each other, and we have the arctan of the square root of x. Now we have the tangent of the arctan. Well, that looks like it's going to undo each other as well. And so in simplifying this y, and in looking at the 7 layers of the chain rule that we would have had to do, since we had a bunch of function inverses being composed with each other, we're able to simplify this big, long, complicated expression into this y prime, or this value of y, which is the square root of x. So what's this? The derivative is simply 1/2 x to the negative 1/2 power. And you can be done here, or you can rewrite it as 1/2 square root of x. So I'll take this for an answer. So that was a lot easier than having to do the chain rule in 7 layers. But if you would have done the chain rule in 7 layers and have done it correctly, you can still get full credit for this problem. It just, something like this would have an easier approach if you were to simplify before taking the derivative.